On the screen are the contents of part 2. As you can see, I'm going to talk about different kinds of NMR spectra. There are hundreds of different NMR experiments we can do, but only those that are used most commonly are introduced, including depth, APT, COGI, TOXI, NOGI, ROGI, HSQC, and HMBC. Then in lecture 6, I'm going to talk about biomolecular NMR and spectral analysis. In the end, I'll talk about NMR spectral assignment. As you might have known, one of the very useful NMR spectra is depth, short for distortionless enhancement by polarization transfer, which allows us to quickly recognize protonated carbons in different groups. As you can see, it nicely presents the CH, CH2, and CH3 groups separately in different spectra, with a spectrum that contains all protonated carbons at the bottom. You also see some imperfection in the spectra, which are due to imperfect pulse width calibrated for the experiment. Note that a depth spectrum does not show quaternated carbons, but they can easily be identified by a comparison with a full 1D carbon spectrum that contains them. You've been told that NMR experiments are designed by different pulse sequences that manipulate nuclear spins in different ways. This slide shows the pulse sequence used in depth, where sequence A is for proton channel and X is for carbon channel. The theta Y represents a Y pulse that tilts MX to different angles, which can be 45 degrees, 90 degrees, or 135 degrees. I'd like you to have a bit of understanding about a very useful pulse sequence used in NMR experiments, which is called spin echo, as shown in the bottom figure. For simplicity, it is with reference to a CH-CH coupling only. In the 1H channel, a 90-degree X pulse tilts the M0 from the Z-axis to the Y-axis, i.e. figure 1 to figure 2 at the bottom. After the pulsing, the elements in MXY start spinning anti-clockwise by fundamental equation of NMR. During the first 1/2J delay, the MXY split or dephases into two vectors due to coupling. One of them spins slower and the other one faster. These are equivalent to two components of a doublet in a spectrum. Next, a 180-degree X pulse flips the two vectors simultaneously so that the slower one is in front of the faster one. At the end of the second 1/2J delay, the vectors are nicely faced to the X-axis, as shown in figure 5 at the bottom. In the end, a Y pulse is applied to tilt the MX for an angle theta. The value of theta is adjustable, which can be adjusted according to the type of the spectrum desired. For example, if we wish to record only CH carbons, then the value of theta is kept at 90 degrees, so that there is a maximum polarization for CH carbons and negligible X-magnetization for CH3 and CH2 carbons. How does theta y relate to the signal intensity of different protonated carbons in depth? This can be described by three sinusoidal functions as follows. For the CHs, it is simply sine theta y. For the CH2s, it is 2 sine theta y times cosine theta y. And for the CH3s, it is 4 sine theta y times cosine square theta y. The curves of the three functions can be drawn on the graph with different colors, as shown below, where the black one is for CHs, the blue one is for CH2s, and the purple one for CH3s. For a spectrum obtained with theta y being 45 degrees, it is a summation of the three functions with theta y replaced by pi over 4, which is 45 degrees. And likewise, the other two can also be defined. In fact, some conclusion can easily be made just by looking at the graph. For example, at theta y equals 90 degrees, the values of both the red curve and the blue curve are zeros, and hence the spectrum contains only CHs. On the other hand, at theta y equals 135 degrees, CH2 is negative. CHs and CH3s are positive, which allows us to quickly identify CH2s. The formulae in the yellow box show how each of the depth spectra are calculated. I'll let you work out why they are formulated that way in your spare time. This slide shows a single spectrum obtained by setting theta y equals 135 degrees. As expected, the CH2s are negative. The CHs and the CH3s are positive. In fact, the CH3s can usually be separated from CHs because they are better shielded and hence are distributed on the right-hand side of the spectrum. Note that carbons in deuterated solvents are not protonated, as they don't have protons attached to them, and hence they are not in the depth 135 spectrum. There is a similar kind of NMR spectrum called APT, the Attached Proton Test Spectroscopy. It is similar to depth 135, but contains also quaternary carbons. The APT that shows here is for the molecules shown on the right. As you can see in the expansion for the region around 140 ppm, the spectrum contains 4 quaternary carbons. 3 of them are for the ipso carbons of the 3 aromatic rings, and the other one for that attached to the dimethyl terminal. The next thing we like to talk about is NOE, the nuclear Overhauser effect. It's named after Albert Overhauser, who proposed the idea in 1953. A general theoretical basis and experimental observation of the effect involving only nuclear spins was published by Lionel Solomon in 1955. It is not until 1980s when the NOEs of spins are quantitatively measured after two-dimensional NMR spectroscopy was developed by Richard Ernst, who was awarded a Nobel Prize in 1991. In 1986, the NOEs are successfully used to obtain a three-dimensional structure of a biological macromolecule in solution, and Kurt Withrig won the Nobel Prize for the development of this in 2002. In brief, NOE is a change in NMR intensity when a neighboring nucleus is saturated by irradiation with an RF field, radiofrequency field, for a certain time, usually around 150 to 600 milliseconds, depending on the size of the molecule. In other words, the populations of a nuclear spin in different energy levels can be equalized by absorbing radiation of a magnetic field oscillating at the alarm frequency. This is called nuclear spin saturation. Note that saturated spins are spinning dipoles. When the spin is saturated, the nearby spins must be affected, and this effect is called NOE. The NOE can be measured when we compare an NOE spectrum with one with no NOE irradiation. When spin J is saturated, the NOE or spin I, denoted here by eta ij, is defined as follows. Eta ij equals mij minus m naught divided by m naught, where mij is the magnetic moment of spin I when spin J is saturated, and m naught is the magnetic moment of spin I when spin J is not irradiated. With a bit of rearrangement, I'm sure you should be able to work out the equation for mij on the right. Factors related to NOE. 1. Gyromagnetic ratios. Between two nuclear species, I and J, the maximum NOE enhancement is related to the gyromagnetic ratios, so that Mij equals m naught times bracket 1 plus gamma J divided by 2 gamma I. Apparently, NOE can be significantly enhanced. For example, it can be used to observe quaternary carbons by saturating a nearby 1H. An NMR experiment that applies this principle is called HOESY, H-O-E-S-Y, short for Heteronuclear Overhauser Effect Spectroscopy. And finally, for homonuclear NOE, the enhancement is 50%. For example, MHH equals to M0 times 1 plus gamma H divided by 2 gamma H equals to 1.5 M0. Okay, factor number 2, molecular weight. No G peaks are negative for sample with molecular weight less than 800 daltons. They are positive for molecular weight greater than 1500 daltons. They are hard to be observed for molecular weight between 800 and 1500 daltons, which is why NOEs for small molecules are much harder to be observed than those for macromolecules. For example, 2D NOGI, short for nuclear over-Hauser effect spectroscopy, for a protein usually looks much nicer. Factor number 3, correlation time tau c and the distance between the nuclei r. It says that Mij is directly proportional to r to the power of -6 times a function of tau c. Therefore, NOE is directly proportional to the distance between two spins, which is why NOE allows us to work out 3D conformations of molecules. Here is the power sequence for a 1D NOE experiment. It starts with a continuous with irradiation of a specific nucleus with its NMR frequency until the spin is saturated. And then apply a 90-degree pulse, P1, to tilt all the other nuclei from the z-axis to the xy planes for acquisition of signals. It is a very simple power sequence. It contains a saturation and a pulsing for acquisition. On the right are the information of an important NMR techniques called phase cycling, which is a method that lies at the very heart of almost every NMR experiment. This process involves repeating a power sequence with judicious changes to the phases of RF pulses and to the routing of the data received. The aim is for desired signals to act coherently with pulsing, whereas all other unwanted signals cancel at the end of the cycle and do not appear in the resulting spectrum. Here, it means that for every 8 scans, pulse 1, P1, is pulsed alternately with different phases, i.e., the first 2 scans are pulsed on the x-axis. The third one and the fourth scans are pulsed on the x-axis, etc., etc. And the receiver routing are also changed accordingly. Here, a 1D NOE spectrum is laid on top of a normal 1D NMR spectrum. The spectra are for 2-ethyl 1-indenone, as shown on the slide. Note that NOE is a through space effect, not a through bond effect. It is directly proportional to the distance r to the power of -6, and hence the NOE intensity per nucleus of a pig indicates a relative distance from the nucleus it represents to the nucleus irradiated. The strongest negative peak in the NOE spectrum is due to the saturation of H3.1, which is the spin J irradiated. As you can see, spin J only induces two strong NOEs, one from its geminal partner and the other one from H2. The rest of the H's are simply too far away to be affected. The NMR assignments here were verified with 2D NMR, which we will talk about soon.